Hello again. Our bell ringer today is this question, or a few questions. How do you know fewer colors can be used on a map? Remember we were talking about the different regions on a map that are adjacent or share a border with one another, how they have to have a different color. Let's think about this. How do you take into account all the possible shapes and sizes of different regions and the way they can come together? And how do you begin coloring a map so as to use the least number of colors? Well, let's just look into that. Stop the video here, and I want you to think about that. And think about the maps. If you have a map handy, look at that map, and you can see the maximum number of colors necessary to color all regions a different color that are adjacent to one another. And when you look carefully, you'll see that number, and we'll talk about what that number is called. All right, let's move on. All right, let's see. Good things. Tell us about something that recently happened to you or to a loved one. Yesterday, I talked about some encouraging words I got from some people. I make videos here, but I also make videos on another channel. And I was personally given some really good encouragement about one of the latest videos I created. I didn't do any talking in it at all. I didn't have any script writing or anything. I just took some videos and added some music to it, and I just played it. And I was told it was probably one of my best videos. Probably not the best viewed video, but that's beside the point. These videos are real easy to make because they're just slideshows and I'm talking to them. Some of the other things I videotape, like sunrises and work that gets done around my farm. Some people might find that very uninteresting, but a lot of people do find it interesting and they like to watch that stuff. And I get a kick out of taking videos of them. So let's go back there real quick. If you have some good things to share with me, please. I'm running out of things to talk about that are good, and I've got a whole year of these videos I've got to make. So if you have some good things, send me a message. Let me know what's good's happening in your life, and I'll be sure to share it in one of my future videos. Have a great day. And let's continue on with the lesson. All right, so learning objective today is very similar to yesterday's. I can create graphs conforming to specific coloring properties, and I can use graph coloring to model a scheduling problem. All right, so let's revisit the map coloring exercises from student activity sheet 9 in terms of graphs. So for example, map 1 can be represented by the following graph. This graph should include a vertex for each country, 1, 2, 3, 4, 5, which we do 1, 2, 3, 4, 5, or region in your map. If two countries share a border and need to be colored differently, the graph shows an edge between the vertices that represent them. So in other words, this edge represents a shared border. So let's check and see if it works. So 1 says it shares a border with 2, 3, 4, and 5. And guess what? 1 shares a border with 2, 3, 4, and 5. 2 right here. 3 right here, 4 shares a border right there, and 5, since it wraps all the way around, 1 shares a border here. Now 5 only shares a border with 3 of them. Or does it? It shares a border with all of them. 5 shares with 2, shares with 1, with 4, and with 3. And that's true. It surrounds all of them, and all of them are, none of them are landlocked. In other words, they're not separate from 5. So, well, how about 4? 4 says it's only connected to 5, 1, and 3, which means that it's not connected to 2. And as you can see from here, that's correct. 4 is connected or borders 1, it borders 5, and it borders 3. So it's a pretty good model for this particular map, and it's just a graph. Using Euler's methods, he made a graph to theorize the map situation, hence the word graph theory. Okay. After studying the relationship between map 1 and the graph for map 1, can we create a graph that represents map 2? So the first thing we need to do is, how many vertices do we need? Well, there's 5 regions, so we need 5 vertices. So let's revisit map 2 again. What regions does region 5 share a border with? All right, so if you follow my cursor, it shares one with 1, it shares one with 2, and it shares one with 4. But it does not share one with 3. 1 shares 1 with 2 and with 5, but it doesn't share 1 with 3 or 4. 2 shares a border with 1, it shares a border with 3, and it shares a border with 5, but it does not share a border with 4. Now 3 only shares a border with 2 and 4. And then likewise, 4 only shares a border with 3 and 5. I'd be interested to see what that graph looks like. Well, guess what? It doesn't look much different than the other one, but has a lot fewer edges, right? See how 1 only touches 2 and 5? See how 2 touches 1, 3, and 5? 5 touches 1, 2, and 4, but not 3. And 3 only touches 2 and 5, and 4 only touches 3 and 5, just like we had discussed. So this is a great example of a graph that represents this map situation. All right, let's restate the map coloring problem for student activity sheet 9 in the terms of graph coloring. You are now the publisher of a new edition of the World Atlas. As you prepare the different maps for printing, you need to make sure that the countries adjacent to each other, those that share a common border, are given different colors. So is it A, color each edge so that any edge that touches more than one vertex has to be a different color? Color each edge so that any edge that touches more than one vertex has to be a different color. All right, how about this? Color each vertex a different color if it has an odd number of edges than those that have an even number of edges. That's kind of strange. We weren't even talking about the degree or the number of edges that go into that particular vertex or their oddness or evenness. So how about C? Color each vertex so that 2 vertices sharing an edge are colored differently. You know what? We just said that if 2 vertices share an edge, it's the same as 2 regions on a map sharing a border. In that case, we'd have to actually color them different color regions, right? Well, C looks like a good answer. Color each vertex so that the 2 vertices sharing an edge are colored differently. That is a great answer. How about D? Color each vertex so that any vertex that it shares an edge with are colored alike. No, we don't color regions the same color on the map, do we? It makes it a little difficult. All right, which of the following graphs require only 3 colors but not less? A, this vertex touches 3 different regions. So this would have to be a different color than this. This would have to be a different color than this. And this would have to, well, not necessarily. Yeah, because it shares a border. But this region could not be the same color of any of these 3. And this could not be it could not be the same color as this one or this one, but it could be the same of these 2. You see that. Likewise here, this vertex would have to be a different color than this vertex and this vertex, but it could be the same as either one of these 2. So let's count how many we got. This has to be different from this, so that's 2. Notice that these 2 don't touch. They could be the same, right? But if we do that, that would give us 1, 2, 3, 4 colors, all right? And that wouldn't foot the bill. How about we do this? We'll make this color, let me back up. We'll make this color, all right, different from this color. And we'll make this color different from these 2 colors. Either way, it'll only get 4, so that's not going to work. Now B, this one's pretty simple. This color can be the same as this, and this color can be the same as this. That would fit the bill, but it would only require 2 colors, so it doesn't fit that requirement of only 3 colors, but not less. Now, how about this? This has a branch to every single one, so it would have to have 5 different colors because all of them have a branch to each one or an edge. I'm sorry. So they would all have to be 5 different colors. And then D, let's look at this. This one has an edge to each vertex. This one has an edge to each vertex. This one has an edge to each vertex. So it looks to me like we have to have 4 different colors. Is that true? I think it's true. Well, if that's the case, then it doesn't look like any of these fit the bill. Let's revisit A. 1, 2, they're adjacent. That's still 2 because these could be the same, right? And then 1, 2, these could be the same. Oh, these could be the same because they're not adjacent. So that's still just 2 colors and then a third color. So A is your answer. All right. So let's create a graph that will be colored with 2 colors. As long as I can't move this around. I thought I could do this. It doesn't give me the opportunity unless I actually stop it. I guess I could, but it wouldn't be as much fun. As long as I keep these you see, I keep all these vertices every other, I can do it as much as I want. That's how you do a graph with 2 colors, okay? And you can continue this on like legitimately as long as necessary. You see how it works? And I can continue and continue and continue. But what kind of teacher would I be if I did all that, right? So let me finish this up real quick. You see they're all in order here. Looks like I have 1 too few, 2 too few, these little sticky things. So you get the idea. I would have to actually have edges. Let me do that real quick. And voila, we have what we call a network where we only need 2 colors. And look at the number of vertices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Possible. So there you go. All right. Let's keep going. What types of graphs can always be colored with 2 colors? Graphs that are odd-gons like triangles, 3 sides, pentagons, 5 sides, heptagons, etc. Is that true? Well, let's look at an odd-gon. If you have a triangle, in other words, a graph that has 3 vertices and edges going just around the circle, 3 sides would work. You'd only need 2 colors, or would you? You need 3 colors because if you look at it, we'll go back to this. Let's just say we had an edge here. They couldn't be the same color because they're connected. So we'll just keep going. 5 sides, same thing. 7 sides. All right. How about even gons like squares, hexagons, octagons? Now remember, how many different vertices do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's not per chance. That's actually true. The answer is if you have an even gon, like a square or hexagon. That is exactly how you can do a graph that can always be colored with 2 colors. All right? So, well, I'm not going to do this one. That's a little more difficult. We'll work on that together in class if we need to. I think you can figure it out. All right. When might a graph not correspond to a map? That's a little more difficult to look at. We'll check it out here in a minute. Okay. Is it possible for a graph with 20 vertices to have a chromatic number of 2? Uh-oh. What's a chromatic number? Let's look up the definition of a chromatic number. Okay. So if you're not familiar with what a chromatic number is, we need to look it up. Chromatic number. Use your resources. All right. Math World calls it the smallest number of colors needed to color the vertices so that no 2 adjacent vertices share the same color. You can also say it is the smallest value of possible colors needed to color a map with all regions that are adjacent to having different colors. So that is a chromatic number. Is it possible for a graph with 20 vertices to have a chromatic number of 2? If so, does it have any cycles? Well, I don't know. Let's look at it this way. How about a tree diagram? Doesn't that keep edges or borders from crossing? Yes. Each vertex is connected only to those of the previous and following levels. So by alternating colors for each level, you can use two colors to color this graph. So you see this, level 1, color the vertex with the first color. Level 2, color all these vertices with the second color. Level 3, use the first color again. Here's another example. A possible shape is a graph that looks like 20-sided polygon and uses only two colors. And notice that the graph alternates colors as you go around the graph until you get to 20 vertices. All right, how about a scheduling problem? Mrs. Jacobs, the new principal at Riverdale High School, wants to make a good impression by offering a lot of new exciting classes for her students. The principal plans to use her knowledge of graph theory to determine when each class will be offered. Now, since she's trying to make her students happy, Ms. Jacobs does not want to offer two different classes at the same time if there are students wanting to take both. She decides to construct a graph in the following way. Each class is represented by a vertex, and if there is a student interested in the two classes, those two vertices are connected by an edge. It's an interesting way to look at it. All right, suppose there are 5 classes, A, B, C, D, and E, and only 5 students wishing to take the following classes. Jason wants to take classes A and E. Emery wants to take classes B, C, and E. Felicity wants to take classes A and D. Jeff wants to take classes B and C, and Hillary wants to take classes D and E. We are tasked to construct a graph for the principal. Use the classes as vertices and use edges to denote students that want to take multiple classes. So if a student wants to take 2 classes, we have an edge between them. So in other words, Jason wants to take classes A and E. There will be an edge between vertices A and E. Let's take a look and see how that works out. This does very much fit the bill. So A and E, Jason wants to take classes A and E. So this edge right here represents Jason's desire to take both of those classes, A and E. Emery wants to take classes B, C, and E. So B has a connection to C, and B has a connection to E. So these two edges represent what Emery wants to take, and so on and etc. Felicity wants to take A and D. This curved thing is for Felicity. Find the chromatic number of the graph and color the graph with the least number of colors. Well, how many colors does it take? Let's see. There's at least 3 because A and D has to be a color, and then A and E has to be a different color. So there's 3, but A and B can be the same color, and D and C can be the same color because they're not adjacent. Okay? So does that make sense? That means that the chromatic number should be 3. Color 1, color 2, color 2, color 3, color 3. And I'm right. It is only a 3-color chromatic number. All right. How can the graph coloring solution help the principal with their scheduling problem? Each color can correspond to a different time. Therefore, with the coloring in question 11, the principal knows that she needs only 3 different times to offer the classes. One possible solution is as follows. Class E, color 1 at 9 a.m. Classes A and B, color 2 at 10 a.m. Classes C and D, color 3 at 11 a.m. It is assumed that each class is only an hour, and that is a good solution. All right, launch. Mathematics knows no races or geographic boundaries. For mathematics, the cultural world is one country. That's David Hilbert, German mathematician, circa 1862 to 1943.